Hi, morning everyone. Thanks for getting up this early. Welcome to Practical Attacks on DOCSIS. My name is Braden Thomas. I'm a security researcher at Activon, where I typically work in embedded device security, reverse engineering, and exploit dev. But today I'm talking about DOCSIS, which is not really, one of those things, and I don't have a background in it. It's just something I've done some research on and I found really interesting. If you have been hiding under a rock and you don't know what DOCSIS is, it's the Data Over Cable Service Interface specification. Essentially, practically, it's just an RF protocol that is underneath those IP packets your cable modem is sending to and from the internet. This presentation is about this protocol. It's not about cable modems or cable modem hacking or any particular cable modem. While that's interesting, there's a ton of cable modem manufacturers and they're all different. So this has a little bit more of a widespread impact. In particular, it's applicable in the United States, Europe, which has Euro DOCSIS, which is mainly layer 1 differences, and Japan. Okay, so what's the motivation? A lot of people, myself included, have tried Wi-Fi attack tools to get access to maybe our neighbor's traffic. The problem with these Wi-Fi attack tools is if you're in a house, you can probably only access the networks of the 2 or 3 houses nearest you. But if you're doing this over DOCSIS, you can probably access the 200 or 300 houses next to you. So DOCSIS, in my opinion, is kind of a cooler way to get access to your neighbor's traffic. What does the network look like? Well, you've got your router in your house, which is in the specs, it's called CPE, or Customer Premises Equipment. And that connects to the cable modem, which is CM, which forwards packets to and from the HFC, which is the hybrid fiber coax network, where it reaches a CMTS, which is a cable modem termination system. From a protocol standpoint, it's interesting to note that the layer 1s are different. The upstream and the downstream physical layers are distinct. And that's because they have kind of different use cases. The downstream physical layer is for the CMTS broadcasts downstream data to all the cable modems. And so it's one to many, so it's continuously modulating data at 64 or 256 quadrature amplitude modulation. The upstream is different because you have all those cable modems trying to send data to that one cable modem termination system. As a result, it's TDMA, which is time division multiple access. So each cable modem is given a small slice of time in which it can send a burst transmission up to that CMTS. And it uses a variety of different modulations, so QPSK, 16 to 64 level QAM. And actually, it's interesting, the modulation that's used depends on what kind of data the cable modem is sending. On top of this, it's an MPEG transport stream in the downstream case, which I'll talk about more in a second, and then a physical media dependent sublayer on the upstream case. It's not very interesting. But above that is the MAC layer, and the MAC layer primarily just defines what kind of packets are above it. And so you have a packet PDU, and this holds your IP packets, any higher layer application data. And then there's some other MAC packets, but the most interesting other one is called the MAC management packets. And there's a bunch of different MAC management protocols. The one I'll be speaking about most today is BPKN. So just to dig a little deeper on some of these protocols, I mentioned MPEG transport stream is used for the downstream layer. And if you think about the way DOCSIS kind of evolved, it's going over the same cable networks that video streams are going over. So it's actually also uses like an MPEG-1 transport stream, which is 188 byte fixed link packets. And 4 of those bytes make up a header. And in that header is a PID. And that PID is kind of like a logical channel identifier. So you can imagine this will be on a single physical channel, but you might have multiple video logical channels on that. And then one of these channels is actually a fixed channel identifier for DOCSIS. In the case of downstream, where you have this continuously modulating data, this continuous stream, this is where desegmentation occurs. So if your packet's longer than 188 bytes, as most of them are, desegmentation will occur at this layer. And then above that is the MAC layer. So I mentioned it kind of just primarily defines what is above it. So there's a frame control byte that defines what kind of packet this is. But it also supports an extended header, which has support for like TLV style data, which will be useful for other things I'll talk about in a minute. So how do you get access to this network? It's cool to know it's there, but you want to actually sniff it. It's distinct depending on whether it's downstream or upstream because they're different, different formats. So there's a few options. The first kind of most obvious option is a hacked cable modem. And I kind of threw this option out to begin with because it'd be model specific to that cable modem. It's kind of clunky because, the software may change. It might depend on a specific version of modem software. Manufacturer may update it, etc. The next option is an SDR, which is possible, but I went ahead and went with dedicated hardware because it's cheap on the market right now and it just works. So what I got is a clear QAM dongle. This pictured here is called a Mijka USB QAM HDTV tuner. It's only $29 on Amazon, so if you're interested in hacking on this stuff, you might go ahead and buy one now to have. And it's cool because it's supported totally out of the box by the Linux DVB API, which is used by Myth TV and any kind of Linux TV software, so that you can plug it in. You can get your unencrypted, clear video channels using this hardware. Accessing the upstream is a little bit more complex. Hacked cable modem probably is out of the question because while cable modem modulates, at these frequencies and with these modulation types, it doesn't necessarily demodulate. Maybe you can hack it up to do that, but a hacked CMTS, cable modem termination system, would probably work a lot better, but those things are super expensive, and it would be specific to that exact model. An SDR is really your best or only option here, because as far as I know, there's no dedicated hardware dongles that let you access the upstream. There's some dongles that will access those frequencies, and other dongles that will, that support those modulation types. But I couldn't find an intersection of the two. But if you know of one, let me know. So now let's start talking about security. DOCSIS sec or BPI+. So all this data from your neighbors is flowing into your house. You want to get access to it, but it's encrypted. And it's encrypted with DOCSIS sec or BPI+. So originally in DOCSIS, they introduced BPI, called the Baseline Privacy Interface. When DOCSIS 1.1, 2.0 came out, it was renamed to BPI+. And then more recently with DOCSIS 3.0, it was renamed yet again to DOCSIS sec for security. So revisiting our protocol diagram, what does DOCSIS sec actually protect? The only thing it protects is part of that packet PDU header, and then the IP and above data, that user data that is coming from your router. The key management part of it is in that BPKM protocol I was talking about earlier. What is BPKM? So BPKM is the Baseline Privacy Key Management Protocol. It's just a client-server key synchronization protocol. It's quite simple. The keys are represented by SAIDs, Security Association IDs, which are just 14-bit random integers. They're not secret. They're exposed in the clear. They just allow the CMTS and the cable modem to know which key is being used. And BPKM performs two operations. The first is authorization. And obviously cable ISPs care a lot about this because they want to prevent cable theft. And one way to do cable theft is by spoofing. So by cryptographically identifying modems using a certificate that's embedded on the modem that goes up to a trusted CA, they can ensure that you can't spoof your neighbor's modem just with his MAC address. We don't really care about this part of it too much because, as I said, this talk isn't about service theft. It's about hacking your neighbors. So we don't care about this too much, except in the way that it protects the next part of BPKM, which is traffic encryption key provisioning, or TEC provisioning. So the TECs are what actually protect that customer traffic that we want to get access to. So let's look at authorization. It's just a single request and response. The request on the left contains some identification info about the modem. So serial number, MAC address, the public key, the full certificate, and then some security capabilities. So what algorithms that modem supports, cryptographic algorithms, and then the security association ID. And if this modem's just booting up, then that'll be initialized to 0. Otherwise, it already has a valid SAID. The response contains an authorization key, though that's encrypted to the cable modem with the key in that certificate, a lifetime and a sequence number for that authorization key, and then those negotiated attributes, so, well, the attributes which currently only contain the negotiated cryptographic algorithm. And then, and that's it. So after that, that cable modem has an authorization key. This request is quite rare. The lifetime, and so this asterisk means as seen on major US cable ISP or ISPs. So that request is quite rare. It has a 1 week lifetime, as I've seen, but if you boot up your modem fresh, it'll do this again because they don't typically store this data persistently. At least my modem doesn't. You also know that this is where security capabilities are announced and negotiated and selected. And that field is totally unsigned, so most likely there's a downgrade attack possible here. It'd be interesting to see some future research on this. But this is not something that I went after this talk. So what are those algorithms? Well, the algorithms that are currently supported are 40-bit DES, which, you know, was for export compliance. It was always optional. I don't think it's really actually been used. I've never seen it used. The standard algorithm is 56-bit DES. And then recently with, well, somewhat recently with DOCSIS 3.0, 128-bit AES. And then the only current data authentication algorithm is none. Okay, so after negotiating your security capabilities, you're going to get provisioned with a TEC, or a traffic encryption key. So this is, again, just a single request and response. So the request contains identification info about the modem, serial number, MAC address, public key, the off-key sequence number, the security association ID, and then this whole packet is HMAC'd with a key derived from your off-key. In response, you get, it repeats the off-key sequence number and SAID to you, but then you get current and next traffic encryption key parameters. So because the traffic encryption key has a lifetime, they give you 2 so that it can kind of gracefully transition between the 2. So there's not this sort of scary period where you might lose connectivity. And these parameters include the traffic encryption key, which is triple DES encrypted with the key derived from your auth key. And then it has its own lifetime and sequence number and initialization vector in there. HMAP again with a different key derived from the auth key. So this provisioning is more frequent, as witnessed on major cable US ISP, that's every 6 hours. As I said, the traffic encryption key is protected with an off-key derived key encryption key. What that means is if I'm just passively observing all of this, I can't get access to it because that off-key was encrypted with the certificate, public key. Another thing to see is that the initialization vector is in those parameters. There's only one initialization vector used for the entire lifetime of that traffic encryption key, and chaining is reinitialized with each frame that the modem or the CMTS send. So what does this actual encryption that I'm talking about look like? Packet PDU encryption. So this diagram shows the packet. It starts at the MAC layer. So you have the MAC header, and this blue means in the clear. So you have the MAC header, which if it's encrypted has to contain this extended TLD header, which identifies that 1, encryption is used, and 2, what security association ID this key belongs to. And next comes the packet PDU header, and it's partially in the clear and partially encrypted. So the source and destination MAC addresses are in the clear, and then the protocol type is encrypted. And the protocol tag would be, IP, ARP, IPv6. And then, so I wrote IP, but just any user data, so it could be an ARP packet or IP and higher packet. And then there's a CRC, and that whole red in the diagram is encrypted with that traffic encryption key. It's encrypted using cipher block chaining, and it uses something called residual block termination, which you don't see too often, but it doesn't use padding. It's kind of the only thing you really need to know about it. Oh, and I should also mention this applies to almost all packet PDUs, but not all of them. Some of them are sent in clear, and I'll talk about that more in a second. So what are the problems that you've probably seen just from me describing the specification to you? First is the use of 56-bit DES. So DOCSIS 3.0 added support for AES, but I have never actually seen AES used on major US cable ISPs. And this is likely due to the fact that they're kind of doing backwards support for DOCSIS 2.0, but you would think because in that authentication stage, the supported algorithms are sent and the CMTS responds with which algorithm it's going to use, you would think that it would pick the most secure one, but it apparently doesn't, because I haven't seen on any cable ISPs that I've looked at. The other thing to note is that CVC initialization vector is reused in each frame sent, and this is required by spec. And that allows drop packets and out of order packets and all that stuff. But the downside is it means that if you send an identical clear text packet, you'll receive identical ciphertext on the wire, and that's useful for some attacks. So now I've described, the specification and what kind of theoretical vulnerabilities we've seen in it. Let's talk about exploiting it. So I first wanted to focus on attacks that were performable only with passive downstream read access. And this is much easier to perform. All you need is that little $29 dongle. You don't need an SDR. There's not really much of a chance of detection because you're not even a cable subscriber, you're not sending any data on the cable network, you're just sniffing. And you could be on the side of the road, plugged into, coax jack somewhere, or an abandoned house, who knows. And so that's the first one I came up with is kind of obvious. It's the DOCSIS DES brute force attack. So there's 3 steps to this. The first is to sniff the network and identify your victims, which is actually, there's a little bit more to it than it sounds like. Then for each victim, you're going to obtain a plaintext ciphertext tuple. And then you're going to brute force the DES key used by that victim so that ciphertext is equal to the expected ciphertext. And ideally, if you can force a static plaintext, then you can use a time memory trade-off. So I'm going to walk through each of these steps. The first is identifying the victims. So I mentioned that the packet PDU exposes the source and destination MAC addresses in the clear. But if you want to actually route traffic to one of these victims, you need to know its IP address because all communication goes to the CMTS, which routes it. However, I mentioned not all packet PDUs are encrypted. In particular, ARP traffic is in the clear. And that's because in the normal startup flow for a modem, IP registration, like communication with the DHCP server and all that, occurs prior to encryption and authentication. And that's unless EAE is enabled, which is called early authentication and encryption, which switches that order. But I've never actually seen EAE used on major cable ISPs in the US. So my approach here is sniff ARP traffic, ARP requests going downstream because they're clear text, and collect the subnets from them. Then from the internet, I send ICMP ping sweeps across those subnets with random varying packet sizes for each IP address in that subnet. And it doesn't matter how that router responds. If the router drops it, it doesn't matter because that packet has already been sent on the coax network and I've already sniffed it with my Michigan dongle. I then perform a correlation between those encrypted ciphertexts that I've sniffed off the wire and the ICMP packet links that I created randomly. And that produces MAC address and IP address tuples. Okay, so the next step is to obtain known plain text values so that we can do the brute force with the time memory trade-off. So you can imagine, this is cipher, this is CBC, so if we send a ping containing some known data, and you look at the way CBC works, the ciphertext at block N, or at block N-1 is XORed with the plain text at block N. And then that resulting XOR goes into the DES encryption and produces cipher at block N. So if we sniff this packet on the wire, and then we resend an otherwise identical packet, but swap out plain text at block N with ciphertext at block N-1, they'll be XORed together, producing 0, and then the resulting cipher at block N, ciphertext at block N, will be the encrypted value of 0. So by that process, we've successfully gathered the static ciphertext for a static plain text, which is 0. I also wanted to mention that sniffing this network is lossy because the modems are able to bond to multiple channels, which means they're listening on multiple physical channels. So you're going to have to resend these packets multiple times, but eventually you'll see them, receive them, and you can pull out that DES at 0. Okay, so now that we have the DES encrypted version of 0, we need a brute force 56-bit DES. And this is not new. In 1998, EFF had the DES cracker. More recently, Moxie Marlinspike in 2012 wrote MS Chapter 2 using some FPGAs. And then Karsten Knoll, 2013, cracked SIM cards using rainbow tables. And then more recently, Sergey and Alex, 2014, reproduced the SIM card attack, but using FPGAs. So when determining how to brute force DES, it's important to keep in mind what the particular use case of the DES encryption is. And in this case, these traffic encryption keys are only useful for 6 hours of traffic. So we want the cracking of them to be cheap, fast, like less than 6 hours, so that we can continuously, say if we want to decrypt our neighbor's traffic indefinitely, we want to be able to continuously crack these traffic encryption keys. So for that reason, it's fine to have some upfront cost as long as subsequent cracking is cheap and fast. So these are the 3 DES attack implementers that I mentioned. Karsten, he described his upfront cost as around 1,500 euro, and his crack time was a minute, less than a minute. Moxie, I didn't see any information on his upfront cost. His crack time is 23 hours. And then Sergey and Alex, I guesstimated their cost based on the cost of the FPGAs they used at about $1,400, and their crack time is 3.5 minutes. Days, correct. Thank you. Big difference there. So I used Karsten's approach because his crack time was only a minute, and that's because he used a time memory trade-off. So I did a similar thing creating rainbow tables to do a time memory trade-off to crack the encrypted version of 0. And I did this all on Amazon EC2, and I stored my rainbow tables in S3. And the total upfront EC2 cost was $2,000 to generate a rainbow table across the entire 56-bit key space of DES. Took about 3 weeks using 100 GPU spot instances. So thank you, Accumont, for approving that expense report. And then, so subsequent cracking cost is, I estimated around 22 cents of cloud computing time. So that's 22 cents for each subsequent key you want to crack, and takes about 23 minutes. And that's assuming that all your computers, your EC2 computers are already spun up, because that takes a while. Mainly downloading the tables from S3. So I have 16 rainbow tables, and they're 64 gigabytes apiece, totaling 1 terabyte. Each chain, which is 16 bytes in that table, represents 1 million DES operations, or what I like to call a mega DES. And so a lot of us have used rainbow tables for cracking hashes, though maybe you don't necessarily have a really good understanding of how they work. At least I was in that boat when I started on this. And so kind of the way a chain works is you take a start value. So this is like an incrementing integer in the case of DES that's unique. And then you're going to encrypt 0 with that start value. So that start value you use as a 56-bit key. You encrypt 0 with that, which will produce an 8-byte 64-bit ciphertext. So you're going to reduce, with a reduction function, that 8-byte ciphertext into a new 7-byte key. And that's your first intermediate value. You're then going to use that intermediate key to do the encryption again. So you do this a million times, binary million times, and you produce an end value. Okay? So then you throw away all those intermediate values, you keep only the start and the end, and that's one chain. So this was my attack platform. I'm going to talk about it a little bit. In the cloud, I had 2 kinds of systems. So I had the Rainbow Table Gen systems, and these are GPU and CPU instances that are creating what I call work units. So each work unit is TeraDes. And if you look at this graph here, so this is Amazon CloudWatch, lets you collect data from your EC2 nodes. The orange line are these work units being created, and the blue line is when they're assimilated. So the assimilator process is the next kind of node I have. This is a memory optimized instance that can download all 4,000 work units and assimilate them into a final table. And each of these tables is 4 petaDes. And that chart goes over just over like 2 weeks. So once we have the finished tables, there's also 2 systems involved in cracking an actual key. So there's the cracker system. And what this does is it's a GPU instance, though you spin up a few at the same time, and it does pre-calculation on that key. So if you imagine the chains that I described, so you have that start point, you have all those intermediate values, so it's a bunch of intermediate ciphertexts and a bunch of reduced intermediate keys, and then you have that end value. So what the pre-calculation step is doing, conceptually, is it's saying, so I have a key. What if that key was the intermediate key at position 1? What would the endpoint be? And then what if it was intermediate key at position 2? What would the endpoint be? So it's collecting all those hypothetical endpoints, and because the chain's 1 million long, that's 1 million hypothetical endpoints. And that process takes about 20 minutes. And then it uploads those 1 million hypothetical endpoints to S3, which is when the table lookup nodes take over. So the table lookup nodes are kind of running for a long time, and they have the finished tables mapped into memory. And they download that list of 1 million hypothetical endpoints, and they perform an intersection of those hypothetical endpoints with the actual endpoints in the table. So that'll produce some list of endpoints that match. And for each matching endpoint it finds, it'll then take the start point, because each chain is an endpoint and a start point, walk up from the start point to where it believes that position, that hypothetical key should be, and see if it matches the actual key. And if it does, then success, you've cracked the key because one step earlier in the chain was the key that corresponds to that ciphertext. And that takes generally about 3 minutes, though, obviously it depends on how many hypothetical start points were found in the table. So also I just want to mention that due to the fact that rainbow table generation is lossy, cracking success is not guaranteed. Even though I put in 2 to the 56 inputs, there is the probability that because we're reducing in every single step in the chain generation, 8 bytes to 7 bytes, we're throwing away data. So there is a probability that 2 ciphertexts will reduce to the same key in that reduction step. One of the things about rainbow tables is that you use the position in the chain in the reduction function, and so that reduces the probability that 2 chains will collide and then meet up. Because unless they reduce to the same key at the same position, then they'll diverge again. But we've been doing this tons of times. So in practice, I saw about 4% endpoint collisions in a table part. Okay, and just one more slide on performance, because you can't even do any of this at all unless you spend a good bit of time doing performance optimizations. Going into this, I really had no experience doing optimization of CUDA, so it was a bit of a learning experience for me. But the most important thing here is bit slicing. And bit slicing allows you to do parallel DES operations. The number of operations you can do in parallel depends on the architecture of the system you're doing this on. And that might be 32 or 128 bits. And so you probably heard about bit slicing, but it actually understanding the way it works, it's kind of like makes you have to switch your mind around. And the way it works is, so if you imagine, DES operation, it operates on a 64-bit data block, okay? So when you hear that, you're probably thinking about like an 8-byte char array, or maybe a 64-bit integer. So that would be a serialized representation of DES. With bit slicing, what you're doing is instead of representing that data block in 64 bits, you're taking each one of those bits and you're representing it in its own variable. So you've got the bit 0 variable, the bit 1 variable, the bit 2 variable, and in each of those variables you just have that 1 bit. And the benefit here is that it makes bit shuffling operations free. So if you imagine if you had a 64-bit integer and you wanted to take bit 20, shift it into bit 3, bit 17, shift it into bit 19, and on and on and on. Each of those shuffles, you would be ANDing that bit, shifting it to the correct position, and ORing it into the target. Repeated. So that would be like 3 CPU cycles for each shuffle. But with bit slicing, you don't even have to do this operation. You just wait until the next operation, and you just say, instead of the bit 20 variable, I'm going to refer to the bit 3 variable. Instead of the bit 19 variable, I'm going to refer to the bit 17 variable. So it kind of makes that shuffling operation free. And so once you understand this concept, then you can start understanding how the parallelism works. So if you imagine now that we have each bit stored in its own variable, wow, that's super wasteful. We're only storing 1 bit in that variable. Let's use up the entire architectural size of that variable. So if the processor supports 128-bit variables, we can operate on 128 data blocks simultaneously by saying, key 0 corresponds to bit 0 in all those variables. Key 1 corresponds to bit 1 in all those variables. So this is kind of a high-level description of how it works. Another thing that's important is this is not just encryption. This is encryption and reduction. So it's important that you bit slice your reduction algorithm. So I replaced addition with XOR, which is more bit slice friendly. And if you don't do this, then you would have to serialize and deserialize your bits between each operation, which would be incredibly costly. Okay, so say we've succeeded, we brute force the key, we now have the traffic encryption key. What about the initialization vector? So that initialization vector was only sent once in the key reply, and maybe we just popped open our laptop and connected to the network, and we're trying to crack existing keys. So we didn't necessarily record it, or we just don't care to keep those. It's fine to ignore those, and you'll only lose the first block of plain text, because if you think about the way CBC decryption works, that initialization vector, all it's used for is to XOR with that very first decryption operation. But if you're like me, maybe you're a little bit OCD, Wireshark hates your PCAPs, and you want to look at these giant decrypted PCAPs in Wireshark. So what you can do is you can determine the IV heuristically. And the way you do this is if you imagine, and I'm sure you've all looked at some PCAP dumps in Wireshark, the most common packet you'll see is just a big 1500 byte IP packet, at the MTU, because HTTP requests are huge. So what those packets look like in the clear is you've got the IP protocol type, you've got the IPv4 version, header length, DSF, whatever that is, and then that 1500 length. So by looking at the ciphertext, you can look at the length. You can say all these packets are very likely to be this IP packet with 1500 length, and then you can heuristically do XOR to determine the IV, and then once again, Wireshark will like it. The IP identification number you can't determine heuristically, but it really doesn't matter because it's an opaque 16-bit integer. Now it's XORed with another opaque 16-bit integer, so who cares? If you really care, you can brute force the CRC. But okay, so now I'm going to show you a video demo of some software I wrote that performs all of this. I'll kind of describe it as explained. Wow, that's really terrible. Here, I have a I have the original source video. See if it's any better. Nope. Okay. Well, I'll just talk through it. Okay. So I'm giving it a C channel here, so that it doesn't have to do the full channel scan, which takes a while. Starting off at 2x, it's listening on the network. So immediately on the left, you see all the MAC addresses of the modems that it's seen, followed by the security association IDs, followed by the number of bytes seen, and then when the last time it saw. So at this point, it's gathered enough information. It's starting to do subnet ping sweeps. So it's currently pinging across one of the subnets it saw from ARC traffic, and then it's going to do correlation to determine what those IP addresses are. So you see it's discovered 6 IP addresses that correlate to those MAC addresses. It then found the DES encrypted version of 0. So blue here means that it's been sent up to the cloud for cracking. So at this point, pre-calculation is occurring, and so I speeded up to 20x here because the cracking part takes a while. And you see it's continuing to do correlation to find IP addresses associated with those MAC addresses, to find those encrypted version of 0, and then to crack the text. And you see it did crack one text so far, and now another. And so really the performance here is kind of just limited by how much money you're willing to spend in terms of parallel EC2 nodes that are running. If you want to run a ton of them, you can crack all these simultaneously. But I limited to kind of a more reasonable number. I think I had like 10 pre-calculated cracker nodes running and like 8 lookup nodes running. Okay. So it's done. I only ran this for a short period of time, but eventually, it would continue to crack more and more text. And when you shut the software down, it then uses the text that it cracked to decrypt the PCAPs, the encrypted PCAPs that it collected. Okay, so that's basically all I'm going to say about that attack. Next, I'm going to talk about a couple of other attacks, which are still theoretical. I haven't successfully performed them yet, but I think they're very nearly practical. And these attacks work regardless of the encryption algorithm. So we can imagine in the near future, these ISPs will shift over to supporting AES properly. And so these attacks will be more important. And the fundamental idea behind them is that you use the cable modem termination system or the cable modem itself plus the ICMP protocol as a decryption oracle. This attack is an active attack. So it only works for the lifetime of the traffic encryption key, and it requires functional ICMP to and from the victim, and it requires being a cable modem subscriber. So all of these are kind of drawbacks from, the brute force attack, but it works in case of AES. So the way this works is if you think about the way ICMP echo request works in the cable modem network. Your router is going to send an encrypted echo request, encrypted with its TEC, to the CMTS, who decrypts it, re-encrypts it with the victim's TEC, sends it back downstream. The victim receives that encrypted echo request, decrypts it, sends it to the router, router replies, gets encrypted with the victim's TEC back to the CMTS, and then decrypted and re-encrypted back to the attacker. So this decryption oracle works by taking that encrypted downstream echo request, modifying it, and re-injecting it onto the network. So for this attack, again, you need to identify the victims, but in this case, you need to collect the encrypted payloads that you want the victim to decrypt for you. You then send the ICMP echo to the victim. You collect the encrypted ping request. Then you have to re-inject it onto the network, but splicing in that payload you want to decrypt. The key here is this requires a QAM256 modulator, and then you're going to wait for the echo response to naturally make its way back to you, which contains the decrypted data. So in terms of the packets, you have your cleartext MAC header, some of the cleartext PDU, and then the encrypted PDU, IP header, ICMP, echo request, and then some placeholder data. You've collected that downstream. You're going to splice in that sniff data you want to decrypt. You're going to then modify, so that's the modification. You're re-injecting it downstream, and you'll receive it back decrypted. So the key here was that injection, that 256 QAM injection. What is the feasibility? As far as I know, there's nothing preventing this at the physical layer, though it does require very specific hardware. One, you could use a QAM modulator. So there's actually a fairly large number of 256 QAM modulators from like little failed cable companies on eBay that you can buy for pretty cheap, but they're going to require some level of hacking. So these are little like 1U boxes that were designed to do some specific operation, so you'll probably have to hack them up a little. The other option is to use an SDR, which is probably possible since you're just you're just modulating data to hardware, which is not terribly difficult. However, I focused more attention on the second decryption oracle attack, which is the cable modem termination system oracle. So this attack involves sniffing the upstream echo reply, which is sent by the victim, modifying it and re-injecting it from your own modem. And fundamentally, it's very similar. The only difference is you're using the CMTS as the oracle instead of the cable modem. So again, here you're identifying your victims. You're collecting downstream encrypted payloads that you want to decrypt. You then send an ICMP echo to the victim and collect that upstream ping reply. And the requirement here is the ability to sniff upstream. And then you're spoofing that spliced together, hacked up upstream packet with the desired payload in it. And this you can do by hacking a cable modem because it's already doing upstream modulation. And then wait for the echo reply containing the clear text. So what is the feasibility of doing the upstream sniffing? So one thing I sort of glossed over about upstream before is that upstream transmissions occur over different frequencies than downstream transmissions. They occur over what are known as the return frequencies. So this is less than 50 megahertz. So if you're using an SDR, you need to get an SDR that can operate on these frequencies, or in the case of like a Blade RF, which I had, you can buy a low frequency transverter that lets you do that. So the parameters of the channels are actually sent in what are called upstream channel descriptor messages. So you can sniff those, and like for example, this one here is describing a channel. It shows the symbol rate, the frequency, which is 34.8 megahertz, the preamble, and then as I mentioned, it uses different modulation types. So this one, for this particular modulation type, it's a QPSK modulated. And I have not made it much farther past this point. So this is a waterfall diagram showing the signal. I've been working on getting it demodulated with new radio, but it's a little more challenging because it is like a burst transmission type. You have multiple different modulation types on the same frequency. So it's something that I'm currently working on. Now, the second requirement was upstream spoofing from a hack cable modem. So I have a UV modem, and I'm sure all this information is different per modem, but all modems share one thing, is that they're incredibly insecure. So you can telnet, in this case, to some port 640, as user to user, and you get popped right into a root shell on my modem. And so when I explored a little bit about the way the modem does DOCSIS modulation, it's controlled by some entries in /proc. So there's an entry called max CPE. So this is the number of CPE devices for which the modem will forward traffic. CPE, customer premises equipment, your router. So by default, this is 1. Because you start up your modem, it's only going to forward traffic for one router, one computer. You know, if you switch out the computer, you got to reboot your modem. Everyone's done this. But you can change it. You can change it to 2. You can change it to up to 256 on my modem. Then, by default, the modem will dynamically learn the MAC address of the CPE, which is why you reboot your modem and it magically works. But you can also statically add MAC addresses by writing them to this add CPE entry. And that will cause the modem to start forwarding any packets from that source address. So when you start spoofing your source address, all of a sudden the modem will receive it and start forwarding them. The only problem is the fact that it'll be forwarding them encrypted with its own tag. So my approach here was to decrypt the encrypted data that I want to send with my tag and expect the modem to re-encrypt it back to the original. And since the SAID is not in the upstream packet, I believe the cable modem termination system determines it based on the source address. So I've done this, but I haven't received the results I expect. So I'm kind of waiting to get upstream sniffing working to confirm that my modem is sending the data as I expect it to send. So I'm focusing on upstream sniffing currently. One last thing about both of these attacks is CRC validation. If you remember from the very beginning, in that packet PDU, there's a CRC. And that CRC is it's part of the encrypted blob. And the CMTS and the cable modems will throw out your packet if the CRC doesn't match. Since we spliced in a whole bunch of data, CRC is not going to match. Obviously, I don't want to brute force it because that'd be super noisy. So what do you do here? Well, my solution was to essentially, if you think about what the sniffed encrypted data's CRC was, it basically was, it started on the MAC header, and then it immediately started processing that sniffed encrypted data. Now the CRC is a bunch of other stuff. So there's the PDU header that's different, there's the IP header, there's an ICMP echo header, and then what we can do is we can find a collision between these two pretty easily by solving for the CRC. It's a 4-byte value you can put in there, and then once it's all decrypted, the CRC and the SNF encrypted data will match what's expected, and that'll work. Okay, so just to conclude here, the DOCSIS network that you are probably connected to at home is most likely less safe than the Wi-Fi network you're broadcasting from your house. The difference is way more of your neighbors can access your DOCSIS network. Downstream sniffing is easy with the Mijika dongle, and decryption is certainly possible. Upstream sniffing, I believe, is close, and active attacks, like the two I described, I think are quite plausible. Offensive conference, but one slide on solutions, just for the heck of it. The ISPs obviously should be supporting AES immediately. For modems that are saying they support it, they should probably support EAE to get those decrypted or clear text ARP packets off the network. Maybe they should consider dropping ICMP at the CMTS, though probably other traffic types can be used for the same attacks. But most fundamentally, they need to add data authentication so that you can't splice data together and fix up CRCs to start to use devices as oracles. So, software. I'm releasing all of my software today. The cable table software that is what I'm calling it that you saw the video demo of, you can run it on your Linux laptop. You can use a Mijika dongle or really any Linux TV, QAM dongle. There's a bunch of them to perform this kind of reconnaissance and cracking on the network. It currently supports either local or cloud-based tables, and you can access it, the source here. I just made the repo public like 5 minutes ago. And then there's also the cloud part of it. So this is the software I use all on EC2 to do the rainbow table generation and the cracking. So you can copy it. You can create your own EC2 network to do this yourself. But you'll say, what about the tables? I don't want to spend $2,000. Well, I'm making them available also. So basically, if you're an AWS user, or you set up an account, you can access them. But because I didn't want to send another massive expense report to Accuvant, I marked them all as request or pays. So what that means is that you just pay for the data transfer. So if you're downloading them onto the internet from anywhere, that's about $90 at current prices. If you're transferring them within AWS, it could actually be free. So if you transfer them to within the US East region, which is where I've generated them, then it's actually free. So you can get these tables, the full 1 terabyte for free. Then you can use the software that I'm releasing to do this, and it'll be quite cheap. 22 cents per key plus the spin up cost. That's it. Any questions?
One very exciting question from the front.
Now, I'm just wondering, with Cousins' rainbow tables, you were talking about it was like $1,500 for the setup, right?
Yeah.
So what's the reason to use the cloud where you paid $2,000 plus an ongoing cost? I'm assuming it's with real hardware.
Yeah, he had a lab set up, like a custom built lab. He works at university, so he can do that.
So it would be hard for you to get the hardware.
Yeah, I'd have to buy all the hardware. Whereas they, I don't know. Where they got the hardware from, if they repurpose hardware, but.
And do you think that if someone was to download your rainbow tables, do you have any estimates on what kind of upfront costs they could do to do the cracking part at home?
They can do the cracking part on their own computer. It's going to be a lot slower than 23 minutes, but you can do it on your own computer if you want. Yeah.
Thanks.
And especially if you have a really nice GPU, then it shouldn't be too bad. But probably the most time will be the reading through or reading through the 1 terabyte of data. But one thing that's nice is that the assimilation process sorts the tables. So it's a binary search, like the table lookup only takes like way less than a second.
So in your first attack, the brute force DesCrack, you were pinging the CMs directly so you could generate that known plain text attack.
Yep.
So that requires being a subscriber, right?
I was doing that from the internet.
How'd you get past NAT?
All the cable modems had a IPv4 address. On my ISP, they all did.
Okay. Can you say what providers?
I prefer not to.
Okay. Oh, I had another question too. Sorry. And then the first decryption oracle attack, how'd you avoid stepping over the CMTS when you were generating the QAM signal going downstream? So you said that you.
I did. So those attacks I said are theoretical. I have not successfully performed them. That was probably my #1 reason that I didn't want to do that version of the attack. Why I wanted to do the upstream sniffing attack instead, because I think that part I'm unsure about. But I mean, maybe if my signal was louder than the CMTS, honestly, I don't know though.